Hi, ACST1052 students. This is Doug Fletcher with a worked solution to question 8 in the tutorial on content for week 6 and 7. So in this question 8, we're considering efficient portfolios in relation to a 3-asset portfolio. We've got the expected returns and the standard deviations of those returns in the table, and we're trying to construct a portfolio with an expected return of 5% per annum. And in particular, although there are many combinations we could use to achieve a return of 5%, we want the combination that gives us the lowest possible standard deviation in order to achieve that. We're told the investor, for part A, we're told the investor has $100 to invest in total, and how much should they invest in each asset. Now, I'm not going to consider the $100 until very near the end of my solution. So because really what matters here is the proportion in which the $100 is invested. So I'm going to do this in terms of proportion. Now I'm just going to change over to my scratch pad. Whoops, from here I need to go into the blank document that I have here. And initially I'll just summarize a little bit of information. So if we're considering, and I just need to make sure that oops, I don't have the right control on my pen here. Apologies for that. That's much better. Okay, so if we bring this back to the top of the page, I'm going to summarize a bit of information. And so the expected return for asset A is 0.02. We're also going to have the standard deviation of the return is 0.05. And the weights that I'm going to use, the proportions here, I'm going to call these W with subscript A, B, and C to distinguish them. So in B, we have 0.06 with 0.08, and I'll call the proportion there WB. And for asset C, we've got an expected return of 0.1, a standard deviation of 0.2, and we'll call that WC. And we're told that our target return is 5%, 0.05. Okay, so using the target return, the first thing we can say is that if we combine the returns according to the weights, which we have yet to calculate, then we will rather obtain our target return. So this functions as a constraint on the values of WA, WB, and WC, and we can also use another constraint here, which is that the weights must sum to 1. So we've got our first constraint there, and the other constraint that I just mentioned is that the weights must sum to 1. Now, this being so, we can then re-express WC in terms of the other weights. Like so. And this means that we can take, we can substitute this into equation 1. And so then we'll have an equation only containing WA and WB. So we're taking equation 2 and substituting that into equation 1. Now, when we collect like terms, rearrange this in terms of WB, then we end up with 0.05 minus 0.08 WA, and the divisor initially is 0.04. And so we can simplify this, and that becomes 1.25 minus 2 WA. Let's call that equation 3. And we can use this to get a more compact expression for WC here. So let's actually take equation 3 and substitute that into 2. And then we find that WC equals, actually I'll turn this around, WC equals WA minus 0.25. And we'll call that 4. Okay, so we can express weights WB and WC both in terms of WA, and that becomes most useful when we actually consider the portfolio variance. So our general expression here for our portfolio variance is going to be taking each of the standard deviations. And so for A, 0.05 squared, that's going to be multiplied by the square of the proportion in asset A. And then we'll have the standard deviation for B squared times the square of the proportion in asset B. And similarly, standard deviation for C squared times the proportion of the portfolio in asset C. And then we need to put in these other expressions we have for WB and WC. So I'll calculate these numbers here at the same time. So 0.0025 WA squared. This gives us 0.0064. And then expanding the WB here, we're going to have 1.25 minus 2 WA squared, and then we will have the 0.2 squared gives us 0.04 times WA minus 0.25 squared. Now, when we expand this, calculate it out, collect like terms, we will end up with 0.00681 WA squared minus 0.052 WA plus 0.015. We'll call this equation 5. Now, this is clearly a quadratic for the portfolio variance, and the only variable here is the proportion in WA. So we can find the stationary point. So we differentiate the portfolio variance with respect to the proportion in asset A. And so we'll get twice times the coefficient here, and we get 0.1362 WA, and then minus 0.052. And now we're going to set this to 0 and solve for WA. And so this gives us WA equal to 0.052 on 0.1362. And it's a little arbitrary how many decimals you want to muck about with here. And then once we've got that for WA, we can go back to the other formulae. So we're going back to equation 3 here. So it's 1.25 minus 2 times the value we just calculated. And so then WB comes to 0.48 0.6417, and WC will then be using equation 4, WA minus 0.25, so that's 0.31791 minus 0.25, and we get 0.131791. And because we had our constraint that the proportions must sum to 1 was built in there, and we actually used it in equation 2, those three proportions do in fact sum to 1. And so now we've got those proportions, then we can come back to our $100 portfolio or $100 investment. And so A will have $38.18. B will have $48.64, and C will have $13.18. Okay, so that concludes our answer for part A. Now in part B, I'll just come back to have a look at that. In part B, we were wanting to consider the same situation, but now using the solver in Excel. So I'll just change over to my Excel application. And here it is. So I've got a table of the information given to us in the question. And I've put in here just some arbitrary proportions, which happen to add up to 1. So I've got the sum across that row. And then here I'm calculating the portfolio return, doing a sum product, taking the vector of returns multiplied by the vector of proportions, and then adding those products to give us the portfolio return. And here I'm multiplying the standard deviations by the proportions. I'm squaring those products, I'm adding them together to get the variance, then taking the square root. And so that gives me the portfolio standard deviation in this case. The other things on this sheet I was using for some other fiddling around I was doing because I was interested in the question. But what we need to do is use the solver. And I'll just move this to one side so we can see all the relevant parts here. So what we need to do is minimize the portfolio standard deviation. And so it's this cell E3 for the standard deviation that we're actually working with. We need to minimize that. The cells we're going to change are the proportions, and we're subject to some constraints here. So the first constraint is that we want the return to be, portfolio return to be 5%. And or any constraint that involves a calculated amount, you need to have the calculation in your spreadsheet. So here's our portfolio return here. We're going to set that equal to 0.05. And our second constraint is that the proportions must equal 1. And so we've got the total of the proportions here in our sheet, and we set that value equal to 1. And that's all the constraints that we need, except that we also need to make the individual proportions non-negative. Okay, so don't forget that bit, otherwise you'll get different solutions. Okay, so let's go ahead with this and solve. Now it says it's found a solution, and if we can move this out of the way and see what we've got. And these are in fact the same proportions that we just calculated. So 0.3818, 0.4864, and 0.1318. If you haven't already done so, check this box here to return to the parameters dialog. It just makes it a bit more convenient working this through. And the next one we were going to use is having the return set to having the target return at 7%. So we're going to change this constraint. So that will now be 0.07. That's all we want. So we click on OK, and now we solve. Again, we need to move that out of the way to see what's happening. And notice now asset A has dropped out of the picture entirely. And this is not a surprise because the target return of 7% is actually above the return on asset B. And so asset A with a mean return of 2% can't really make much contribution to that. And its standard deviation isn't sufficiently below 8% that it could still have any influence. So what's happening here is that we're restricted to 2 assets effectively. And because of that, the variance minimization or standard deviation minimization effectively drops out of the picture. And so this 0.75, 0.25, that's just a linear interpolation between the two returns on 6% on B and 10% on C. And that's it, all that's doing. It's a linear interpolation on that, and there's actually no attempt made to minimize the variance at all. And as we move the target return higher to 9% for the last part of the question, we'll find exactly the same situation, except now we'll be much closer to the 10% in asset C, return in asset C, and we'll find these two proportions here are reversed. We should expect 1/4 in B and 3/4 in C, which is again exactly a linear interpolation between 6 and 10 to get 9%. So let's do that. Again, changing this constraint, going for 0.09. We're done with that. That's okay. And solve. And we see once again, that is in fact what we get. Say 0.25 and 0.75. Okay, so that completes the solution on question 8. I'll be doing another solution on question 11